Good evening. I'm Ashley Miley, a student with the University of Washington's Engage program, here to welcome you to our event tonight. As a graduate student, I get a specialized training in how to do a very specific type of research. The Engage program gave me another type of training that graduate students rarely get. I learned how to talk about my science in a way that is engaging, enlightening, and informative. You can learn more about our innovative program at engage-science.com. And now, our guest. Paige Northway is a second-year graduate student in the Department of Earth and Space Sciences. She is currently involved in the UW Rocket Program and hopes to expand the university's involvement in the production of small satellites. Tonight, she will be talking about improving magnetic measurements in space. Please give a warm welcome to Paige Northway.
Thanks, Ashley, for that nice introduction. As she said, my name is Paige, and I'm a student at the University of Washington in the Earth and Space Sciences Department. I hope by the end of my presentation that you guys might have some appreciation of why I'm interested in small satellite magnetic measurements. And just to start us off, I like to say that I'm interested in how to study planets and moons by measuring something that you can neither see nor feel. And I like that tagline a lot, but I read it the other day, and I was thinking, man, that sounds kind of a lot like I'm interested in ghosts. And I'm not interested in ghosts. These things are real, and you may hear magnetic fields, and I know that some of the science, some of the physics behind the interactions of magnetic fields can be a little intimidating, but I promise you they're not as scary as this ghost. So let's talk about magnetic fields. Again, this can be kind of an intimidating topic if this isn't something you're familiar with, but let's back it up and talk about something you are familiar with. Fridge magnets, or magnets in general, are something you might use every day. You might have a grocery list on your fridge. They might be holding up coupons. I particularly have a cookie dough coupon on my fridge right now. And again, it's something you can really easily relate to. It's not something strange or scary. These are everyday things. What else might you think of that is not maybe everyday, but common thing? Well, a compass. How a compass works is you have a needle, chalk, and it aligns with the Earth's magnetic field. We'll talk a little bit more about the Earth's magnetic field in a moment. But basically, if you've ever gotten lost in the woods, a compass is a really good thing to have with you so that you can find your way back out. Now, maybe you remember 8th grade science class, or maybe you play with magnets every day. But a common magnet is a bar magnet. Here we have an example. And around the bar magnet, what we have are iron filings, so little pieces of iron. And the iron, just like the needle on the compass, is lining up with the field lines around that magnet. Now, a few things you can take home from this. It kind of looks like you've got little lines going from one end to the other. And these are sort of an imaginary thing, a concept that we call magnetic field lines. Magnetic field lines, basically they tell you the direction and the strength of the magnetic field. So where they're very dense, there's a high magnetic field. And you can see the direction that the magnetic field is going by following these lines. Now, we're interested in studying planets and moons, right? Why are we talking about bar magnets? Well, that's because you can imagine that the Earth has a giant bar magnet in the inside, and its field, you can see, kind of mimics the lines of the iron filings we saw with the bar magnet. And just like the bar magnet, here at the North Pole and the South Pole, you have stronger magnetic fields, you have more lines closer together, and you have fewer outside. In addition to the strength of the magnetic fields, what's important about the Earth's magnetic field, it has something that we call a global magnetic field. And essentially, there's all the way around the Earth is one sort of magnetic field that you can characterize in a signal, basically magnet. And what that does, why we're interested in that, is because guess what? The sun also has magnetic fields and particles and all sorts of good things that can be harmful to us on Earth. And what our magnetic field does, our global magnetic field, can actually create kind of a little bubble here. If those blue lines are the boundary of where our magnetic field interacts with the sun's magnetic field, and it protects us from the sun from harmful things like radiation and some of the solar particles. So this is actually really interesting to us. Given some strong solar weather, you can have major repercussions with our electronics here on Earth. One other thing about the particles on the Earth is that with the magnetic field lines, you have interactions with particles. They're sort of intrinsically together. And so what I have here is a single magnetic field line drawn in, and the squiggly line is the path that a charged particle might follow. And the way I like to think about this is if you had a string and you have a bead on the string, you can flick the string and the bead will rotate around the string. The bead can go up and down the string and you can move the string, but the bead will always stay on the string. It doesn't go off the ends. And so that's kind of how charged particles move along magnetic field lines and how those two are interacting. And one of the reasons that's important, and something you might recognize, is the aurora borealis, or the northern lights. Now, the northern lights are actually caused when the sun's magnetic field is interacting with the Earth's magnetic field, and those charged particles that are following along those magnetic field lines actually impact into our atmosphere. They get all the way down into our atmosphere, and they make these beautiful colors in the northern hemisphere and the southern hemisphere. I mean, there's lots of interesting phenomena that are related to these magnetic field lines. And now, let's move this outside of the Earth. We're always kind of interested in our own thing. We're a little narcissistic. We care about the Earth. What does that mean for us? But let's move it another planet away. Let's go look at Mars. Why are we interested in what might be happening on Mars? Why could we care about the magnetic fields on Mars? And we believe that at one point, Mars had a global magnetic field just like Earth, that you could characterize it by a single bar magnet going through the center of the planet. Now instead, that no longer exists, but you can kind of pretend that you just took a bunch of little bar magnets and you placed them on the surface of Mars, resulting in, resulting in something that we call umbrella fields. Basically, you have you have beach umbrellas, and you planted them in the surface of Mars, and they're protecting little chunks of Mars, like our own global magnetic field protects the Earth. And there's a few interesting things. This picture that I'm about to put up right here is a map of the surface of Mars, and it's complicated, it's intimidating, but let's break it down. Basically, if you have a lot of colors, you have a stronger magnetic field. If it's gray, you don't have a magnetic field. And the take-home message here is that by looking at the magnetic fields versus where these gray areas are, those gray areas correspond to interesting geographical areas on Mars, volcanoes or craters. And we can deduce by the fact that there are no magnetic fields there, that those things all happened, they all formed, they were all created after Mars no longer had a global magnetic field. So that's one interesting thing. And now, kind of a more cool pop culture interesting thing is that I think you guys have all heard of SpaceX. SpaceX is a private space industry company that is actually about to build in Seattle, which is very exciting, bringing more tech jobs to Seattle. But SpaceX has this grand plan, and they're going to bring internet to the world by launching a bunch of little satellites. And then with the money that they make, because everyone needs internet, the money that they make from selling internet to the world, they're going to build a colony on Mars. And one of the things they might be interested in is putting that colony in one of these essentially umbrella fields so that they can protect the colony better from some of the radiation coming off the sun. All right, so we've talked about planets, but I promised you moons as well. So let's talk about one moon in particular, very interesting in science today, and that moon is Europa. Europa is a moon of Jupiter, one of the 4 Galilean moons, and we got originally some information on the magnetic fields around Europa, and we thought that Europa had a global magnetic field. We thought, hey, this indicates that it has a global magnetic field. And then we got more and more data, and it looked like the bar magnet that we thought was inside Europa was changing direction. And so we're like, wait, what is this? Well, it turns out that can be best described by there being a salty liquid ocean on Europa. And one of the reasons this is really exciting to a lot of scientists is because we think there's a possibility that this could be the best chance in our solar system outside of the Earth for life to potentially grow. And I don't know if anyone's seen Europa report, but spoiler alert, we're not looking for glowing giant squid. We're looking for much smaller life forms that might possibly be there. But we believe that with the icy layer on top and a salty liquid layer, all on top of an active mantle, they could have a habitat that is similar to the hydrothermal vents that we find deep under the ocean here on Earth. So there is a chance that that could actually be a place where life would form. And we've basically corroborated that because of the magnetic data that we have from that. So I've been holding out. There's one thing about magnetic fields that I haven't told you yet. And we have my computer right here presenting. And we plug my computer into an outlet because this computer has bad battery. We need to plug it in. And the outlet over there is connected to the computer by a wire. And in that wire, we have current, where electricity is charging this computer. And with electricity, any currents, guess what? We have magnetic fields. And you wouldn't think this is a big deal, but if you're trying to measure magnetic fields in space, you don't want to measure the magnetic fields that you're creating. And you can see this might be a problem because on a mission, and this is an example of a mission, it's the proposed Europa Clipper, which is supposed to go back to Europa and take more data, potentially proving or disproving that there's this ocean. And the Europa Clipper it's going to weigh hundreds of kilograms. You know, it's this entire group of people combined sent into space. It's a big thing. And then 8 science instruments. There's a whole lot of things that need current, that need electricity. Electricity is going to be running all around on this satellite, and powered probably by about 150 watts of power, which supplies ample current, could supply ample current for you to have large enough magnetic fields to make a big difference in your measurement. So essentially, our big spaceship is putting off a bunch of magnetic fields, and that's not what we want to measure. Let's back up real quick and talk about how we measure magnetic fields. And we use magnetometers to do that. And there's a wide range of magnetometers. There's a number of different techniques of how to measure magnetic fields. I'm not really going to get into those. This here is the big picture, is an example of a magnetometer that's actually currently flying around Mars. And it's called a flux gate magnetometer, and it's actually measuring the magnetic fields in 3 directions. So it's a vector magnetometer. Now, for reference, we also have a little magnetometer up here that's also measuring 3 directions of magnetic field, and it's less than the size of a quarter. And so maybe it's not as robust and it's not as precise, but there's a wide range of magnetometers, and one of the exciting things about them, one of the useful things about them, is that you can use them very low power, very low current, and they can be, like in that picture, they can be very small. So let's go back to what we were talking about. We have this satellite that's got all sorts of electric currents running around it, creating these magnetic fields that we don't want to measure. We want to measure the magnetic fields of space. And so how do we get around that? Well, there's a number of different ways that people have done that. One of the most popular ways to get around that is to take your magnetometer and stick it on the end of a big arm. This is the Galileo satellite, and this is actually the satellite that took that original magnetic data about Europa, the moon of Jupiter. And the thing about this is a really long arm. It's about the size of an NFL goalpost. It's pretty big. And this can lead to problems in cost, in engineering. You can't launch something sticking out that far. So you have to be able to unfold it or deploy it. And in space, anything that moves, anything that has to move, is another chance for failure. Basically, it's another complication, something else that can go wrong. So there's a lot of engineering costs involved with this, although it's very successful and you can get very good data with this. By moving it, the distance of a field goal post away from your satellite, you essentially negate all the magnetic fields that are coming off your satellite. You're far enough away that you don't see those magnetic fields. I don't know if anyone noticed, but this is a Bronco stadium. I moved here from Colorado, so go Broncos. So this is one way. Let's review real quick. One way that we deal with the problem of magnetic measurements in space. Another way that has been used on a few missions is to put the magnetometers at the ends of solar panels. And this satellite is MAVEN. MAVEN is currently orbiting Mars, taking all sorts of good data. Awesome, awesome spaceship. And the magnetometers are actually out here on the ends of the solar panels. And this has been actually more successful than they were hoping for it to be, which is great, but it's not many yards away from the spaceship. It's maybe a few, and actually it's very close to the solar panels, which do have their own currents flowing through them. So it doesn't cost as much, there's not as much extra engineering that has to go into making these magnetometers, but instead you may lose some precision if you're trying to measure very small fields, because you will end up picking up some of the currents that are going through there. So it's a pretty good trade-off, but it's not perfect. And now my final and least favorite method of dealing with the problem of magnetic measurements in space is to not have them. Just don't bring magnetometers. Who cares? That's too much extra cost, it's too much extra work. But there's a number of missions where they've actually looked at particles, charged particles, but not at the magnetic fields. And like I talked about in the beginning, with the charged particles, they're moving along these magnetic field lines. So if you're sensing these particles and you don't have any understanding of the magnetic field in that area, you don't know the origin of these particles. These particles could have come from the sun, they could have been part of the solar wind, they could have come off of a planet that you recently flew by, there's a whole lot of different things, and basically you're missing out on a lot of the science that you could potentially be doing with your mission if you drop out. No cost, it's great, but you are losing some of the possible science that you could be doing with this. So, very quickly, let's review the options that we've gone over so far. You have the Galileo satellite with the long arm, really good measurements, but high cost engineering and possible problems that could occur because you have to extend that long arm. Then in the middle we have MAVEN, where you put the magnetometers at the ends of the solar panels. And this has actually seen fairly good success, but will limit precision because you are so close to these currents. And then finally, if you drop the magnetometers entirely, then you're losing that possible science. It's no cost, which is great, but you are losing some of the science that you can do with your mission. And so, our research is hoping to propose a possible new solution to taking these magnetic measurements in space. And what we plan to do is look into using small satellites. We're going to totally take the magnetometers off the large satellites and put them into small satellites whose only purpose is to make these measurements. And I'm actually currently funded by a NASA JPL proposal that is to look into the possibility of using one of these small satellites to go with the Europa Clipper and take magnetic field measurements at Europa. And so we're doing a concept study of that right now. And CubeSats in particular, I brought a few examples with me so you guys can get a good idea of what I'm talking about. Small satellites. This is what we would call a 1U CubeSat. We have a single unit. And it will become very apparent when I show you a 2U CubeSat. Essentially, we just took two of these and stuck them together. And our Europa proposal is actually for a size of a 3U CubeSat. And so you can kind of see that if you stack these all together, this is 3 units of CubeSat. And this is a very actually up-and-coming sort of popular idea. And so we're hoping that CubeSats are something that gets used a lot in the future. And in order to do that, we have a number of ways that we need to improve CubeSats in order to be effective in these measurement schemes. We already know that magnetometer measurements are well suited. As I said, magnetometers are very low power, so they're easy to put on these little satellites where you can't generate a lot of power. And they're very small, so they're easy to put on these small satellites, simply because they're small. but there are a few advancements that we need in order to make these satellites very useful. And two of those advancements include propulsion. You can see a picture there of a propulsion system with some of the lab in the background. So we have to be able to move these satellites around. If you're trying to communicate with a mothership, or if you have sort of a whole fleet of small satellites, you need to be able to stay in formation, stay near whatever your main mission is. And so that may require you to move around, and you would need propulsion. And so that's one thing that we're working on in our lab. The second is communication. And big shout out to Mariah, who made that SolidWorks picture. And this is basically a picture of a satellite with many little tiny antennas on the back side of the solar panels. And this is an avenue we're exploring because you will have to be able to communicate in some way. If you take all this good magnetic measurement, all this good magnetic data, and you can't communicate it back, then it's kind of useless. So we need to improve our ability to communicate with these satellites as well. And so basically overall, we have a few technological developments that need to be made further in order for the magnetic measurements with CubeSats to be very viable. But in the future, with the current rate that CubeSats are advancing, we can expect to use them either in fleets by themselves or on a larger mission tagging along as a lower cost and no cost to the data method for making these magnetic measurements in space. With that, I would like to give special thanks to Town Hall for hosting me and the Engage program for giving me this opportunity. And then also I would like to mention my advisor, Robert Wingley, and then Ian Johnson and Paul Sturmer, two graduate students that I work very closely with, and also Shelley Chesler, who taught the class that enabled me to speak here today. And with that, I would like to open up space for questions.
Thank you for the nice talk, Paige.
It's really
Why doesn't the CubeSat interfere with the magnetic measurements?
So the entire purpose of the CubeSat would be to take the magnetic measurements. So essentially, you wouldn't have other instruments running currents. And so, like I was talking about with the Clipper, it's got 8 instruments. Some of those are radar, very noisy, very magnetically noisy instruments. And so if the CubeSat was only taking magnetic measurements, it could have essentially everything else shut off while it was taking these measurements. Or you could even extend your magnetometer out just a tiny bit, and you would have no problems with those measurements.
What does it cost to launch one of these satellites? And could just an average, like Seattle Light, have enough money to do so?
I guess it depends on your average Seattleite. But there's actually a company in Seattle whose name I'm blanking on at the moment, but they organize smaller satellites onto bigger launches. So basically CubeSats are flown with bigger launches. If you have a big communication satellite going up, maybe they have some extra room and you get to put your CubeSat on it for a low fee. Through NASA, universities are able to launch for free as long as you deliver on time. But for your average Seattleite, a satellite like this into just whatever orbit was available would be $300,000.
Can you talk a little bit about what you're using for propulsion on the satellite, as well as the Martian magnetic fields? They look like they only have one pole on them, and then about how big are those magnetic fields?
Okay, so the first question was the types of propulsion. And our lab in particular has been exploring something called a pulsed plasma thruster. And there's a few things you have to overcome. Most CubeSats, because they're launched with other things, they're called secondary payloads, and you have to follow all sorts of guidelines, so that really limits what you can use as far as propulsion systems go. And one of the reasons that we use pulsed plasma thrusters is because you have a solid fuel that basically isn't going to blow up. You don't have any potential fire starting mechanisms. And essentially you ablate and accelerate a very small amount of your fuel. And if you can fire it over and over again, you get a little impulse each time, and that speeds you up eventually over time. Do you want more on that? We're also starting to look into Hall thrusters. I mentioned SpaceX, and they're planning on powering their satellites with Hall thrusters. And then the second question was talking about Mars, and I will flip back to that, wherever it went. Okay, so the umbrella fields is just an artist's depiction. I wouldn't worry too much about the poles there. That's not what we're interested in. And then in this picture, what the colors actually are, you have a satellite that's orbiting Mars, and it's looking at the changes in the magnetic field. That's not absolute values of the magnetic field, that's how much it's changing over a change in latitude. And so it is polar, so it goes between red and blue. That's your different poles.
I'm not that familiar with the pulse plasma thruster.
Do you want to see one?
I'm familiar with Hall thrusters. How do you plan to get enough power for those?
So, if you don't have to fire it a lot, you don't need a ton of power. But if we go back, way back, with a solar panel configuration with about a square meter around the Earth, you can get, if you have very efficient solar panels, you can get something like 100 watts. So you can, if you are getting very efficient power conversion, you can power that with no problem. And we have charging, so the way it works is you have to charge up a big potential difference, but it only has to be there for a very small point. It's pulsed. And so it doesn't require constant power, and that allows us to limit how much power we're using. Yep.
I think you talked about what was causing Europa's water basin, basically, around the moon. But what exactly in the magnetic fields do you expect to find, or would you be delighted to find? What patterns, I guess?
Okay.
If you could make a picture.
Well, I wonder if I have something good. So, essentially, the reason we have the data that we have is because Jupiter's magnetic field is tilted, and it rotates with Jupiter, which rotates much faster than Europa travels around Jupiter. And so, Europa field, just like the Earth, and it doesn't. But like I said, currents drive magnetic fields. Well, changing magnetic fields also drive currents. And so as it sees this changing magnetic field, it's driving currents in the salty water that we think is there. And so we'd love to get more information on it, and we could further bound what we think the layer is and how deep we think it is. That's really mostly where the question is. Right now, we're pretty sure there's either slush or salty water there. That's fairly well established. But we're looking for more the bounds of the extent of it and the boundary between the ice and the water. And then if there's any sort of larger features, larger lakes, and if it's not just a nice spherical shell, if we had a lot of magnetic data, we could potentially back that out by looking at the changes that we saw. Does that kind of answer your question? Okay. Well, thank you.